Hey guys, it's Alan again. I know you're getting sick of me, but I'm back to talk a little bit more about diodes. Specifically, this video will cover Schottky diodes and the Zener diode. Let's start with the Schottky diode, which is designed to handle larger currents than the diode that we've talked about before, just your typical p-n junction diode. And one reason that it can handle more current than a p-n junction diode is because it has less internal resistance associated with it. And that's because the Schottky diode is not formed using a p-n junction. It will use only one semiconductor material, let's say the N-type, because electrons are better charge carriers than holes. They'll move faster. So it's most common to use an N-type semiconductor. And at the junction, instead of a p-type semiconductor, you've got an ohmic contact is how they refer to it. It's just a metal. It's a metal contact right there, and this metal allows for less internal resistance, which means less heat as a result of the current flowing through, and faster switching time. And so let's look for a second at our whiteboard. I want to compare the IV characteristics of the Schottky diode to those of the p-n junction diode. So let's see if I can draw this and do it any justice. So here we have got our current, and here we've got, let me extend this, here's our voltage through the diode. Alright, so VD, ID, and let's say our let's use a different color here. We'll be pretty today. Let's say this is our p-n junction diode. Now let's say that's the IV curve. Alright, and what this shows is that it takes up to, let's call this, let's go back to the black here. Let's call this roughly 0.5 volts and this 0.7 volts. So somewhere in this range, you're going to get a steep increase in the current going through the p-n junction diode, which means that, if you're going to get a forward current, when you're going to get significant forward current through the p-n junction diode, you need about this much voltage, somewhere in this range. In fact, it's closer to the 7 volts typically than it would be the 5 volts. So our curve is not exactly reflective of that. But let's look now at the curve for the Schottky diode. For the Schottky, on the left-hand side, it's going to look pretty similar, but the biggest difference is here, where when it has a forward bias, when you've got positive voltage on the Schottky diode, across the Schottky diode, you're not having to wait to get to these voltages before you get a significant current through the diode. And that's because you've got this ohmic contact up against the N-type semiconductor material, and the decreased resistance allows for a near linear IV curve under forward bias. I mean, that's not a perfectly drawn curve, but the concept is shown correctly, that it's going to be near linear here, except for it'll be less so closer to here at very, very low voltages. So that's the Schottky diode, and like we said, it is designed to dissipate, I don't guess we said this, but I'm saying it now, it is designed to dissipate power more effectively than the p-n junction diode, and so they can be used for higher currents because of that lower resistance. Let's go now to the Zener diode, and I'm going to erase this, and we may need, I think we're going to use an IV curve again in a minute to look at this. But let's go back to the slide for a minute. So on slide 12, the Zener diode is very much like a p-n junction diode, except that instead of being designed to operate under forward bias and let the current travel forward through the diode, it's actually designed to operate under reverse bias so that the current will run the opposite direction through the diode. And to understand how that happens, we've got to backtrack a bit and talk about what we did earlier concerning the reverse bias across a p-n junction diode. And we said earlier that when you apply reverse bias across the p-n junction diode, you're not going to get much current at all. You're just going to get that saturation current. And on the IV curve of the diode, let's go to our whiteboard and take a look at that. Let's see what this looks like. Alright, so there's I, and there's our V. Voltage across the diode. And here we've got our IV curve. Alright, now I want you to look at, what color do we want? Let's go with red. Look at this region here. At whatever this, hang on, I said this and wasn't ready to mark it. Whatever this voltage range is right here, we could call that the Zener region. All right. Now, to be more accurate, there's actually such a thing as the Zener knee voltage, which will occur right about here at the knee of this curve, where it begins to where the slope starts to change dramatically, and the ZV. The ZV can change. It could be any one of these voltages. It could be any of these past the knee. All right? But that's the Zener region, and that is the region at which that's the voltage at which a Zener diode operates. The idea is that if you have a great enough reverse bias across the Zener diode, you can cause tunneling or an avalanche of the electrons across the voltage barrier that was created inside of that p-n junction, and that's the Zener diode. At this level of reverse bias, the magnitude of the current can vary greatly, as is indicated by the very steep slope here. The magnitude of that current can vary greatly without causing overheating or a significant change in the voltage. And that's one reason why Zener diodes, not just one reason, that's the main reason why Zener diodes are used in voltage regulating and surge protection circuits. So I hope this has helped, and good luck on the FE.